All right, maybe let's get started. So thanks everyone for joining us. My name is Martin Schubert. I'm the host of this talk. I work at an early stage project at X that touches on both machine learning and physics. We're very fortunate today to have Lingling Fan, a PhD candidate from Stanford, who was advised by Professor Shantui Fan, who's known to many of us here. Before joining Stanford, she earned a bachelor in physics from Nanjing University in China and was also a research assistant in the physics department at Yale, working with Professors Owen Miller and Stephen Johnson. Her interests are in computational, experimental, and theoretical studies of photonic devices, including neural nets and information processing. And we're going to dive into that today with today's talk, which is titled Optical Matrix Multiply Units in Tensor Processing Unit. So just a couple of logistical notes. We're going to record this talk and share the link, so look forward to that. I also have a dory for questions, so if questions come up, please add them. We'll use it at the end and also maybe have time for live questions. And with that, let me turn it over to Lingling for what I'm sure will be a fascinating talk.
Thank you, Martin. Hi, everyone. It's really a special honor to be here. And thanks for introducing me, and thanks for having me here. My name is Lingling Fan. Today I'm going to talk about the optical matrix multiply units in the tensor processing unit, TPU design. So I'm going to talk about three aspects of this topic. As a background, I would start from the matrix multiplication in the TPU system, and then I would introduce some of the photonic components that can be an equivalent systolic array to perform the matrix multiplication. And in the last part, I would like to talk about the systematic implementation for this photonic systolic array in the TPU interface in order to fully utilize the memory hierarchy advantages in the TPU system. So let's start from the TPU matrix multiplication. The artificial intelligence workloads have posed a huge challenge in the traditional hardwares. In earlier years, the AI compute demand roughly follows the Moore's law. However, in recent years, this chart shows that the AI compute demands increase 10 times per year. And this explosion of the compute demand for AI workloads far exceeds our capabilities to build faster processors, even if the Moore's law is alive in the modern era of AI. So from the concerns expressed by many people in the Google TPU team, we are aware that this workload explosion has expanded to data centers, which needs to scale up and develop the next generation of hardwares. So from the words of Professor David Pason talk in 2017, we know that the domain-specific architecture is an efficient way to solve this challenge. So one successful example of this domain-specific architecture is the Google TPU, which has been developed first in 2015 and maintained a rapid progress since then. So each generation of the TPU has shown increased performance with increased inference speed and reduced training time, as well as more and more functionalities. So this is fascinating, and to see this increased performance, and we wonder one of these key reasons for this improvement is this memory hierarchy, where we use dedicated memory to minimize the data movement time cost. And this is also related to the domain-specific application, so that we can use the software-controlled memory to control the memory access time. So this would further increase the speed and the performance of the system. So we would like to inherit this merit from the TPU system and build the photonic system in the TPU design as well. So looking at this processor layout, another point I would like to highlight is this large portion of the matrix multiply units. So from the hierarchy we have shown in the last slide, the matrix multiplication unit is busy every time. So this plays an essential role in the high-speed computation of the TPU system. And we would like to utilize this point to connect to the photonic components embedded in the system. So here we propose that the new hardware based on photonics, and more specifically, the silicon photonics, which refers to the building the optical components at the semiconductor chip scale, utilizing the standard CMOS manufacturing capabilities. So as we would see in the following slide, we have competitive computation density and easier semiconductor manufacturing process. So as I have highlighted here in this yellow box, so we've shown this example of interferometer meshes as the matrix multiplication and accumulation counterparts in the current TPU design. So what we are considering here is specifically replacing the ARU in the with the photonic components while maintaining the memory hierarchy of the TPU system. We would like to maintain the large-scale matrix multiplication towards the 64K scale to compensate the granularity in the detector part. And on the other hand, what photonics can offer to TPU is this vectorized input, so that we can process very large scale data, especially for the tensor processing applications. This would offer a high bandwidth and high speed, and which is in a similar manner for the optical fibers. So as a review, the digital systolic array used in the TPU system has been very efficient to manage the data flow to fetch input data from the memory and maintain the high efficiency in the processor unit. However, as we know that the clock speed is limited and the transistor cannot get any faster, so this serial clockwise data processing manner actually poses a limit in the speed and other performances. So we would like to say, how could photonics do the same job but in a better way? So it is actually realized several decades ago, but at that time, the choice they are considering is some free space components. So it is like in this systolic array introduced by NASA, people have already utilized this acoustical optical system to realize some systolic array computation function, and the parallelism between the input element can be seen as very natural, and they don't have this row by row data flow, and you can solve everything together at one shot. So since we have seen this programmable photonics, as we should definitely implement this systolic array in the photonics to maintain this parallelism in photonics, and this would be very promising for the tensor processing applications. So without going into the specific photonic element, we have this abstract representation of this photonic processing element. We call it as PE. Each element can perform the same functionality for 2x2 transformation and differed only by their weight on site. As we have the programmability, we can easily put the same element globally and change the detail of those elements one by one, use the same control units, which I would introduce later. So the systolic array here is composed of embedded PEs. The entire T matrix, which represents the matrix multiply units using photonics, can perform the matrix multiplication by optical transformation. So it is intrinsically can get this output vector at one shot. So having this abstract representation in the second part, I would like to introduce the detail of the photonic systolic array, where we can also control this using some programmable algorithms. So photonics is common and has played a long-term role in our current technologies. For example, the optical fibers have been ubiquitous in high-quality communications, and these integrated photonics have been actively developed by many mainstream the hardware companies such as AMAG, IBM, and Intel for more efficient data flow and large bandwidth. So in the area of AR and VR, as well as those LiDAR photonic devices have been widely used to collect the high quality data and rendering complex scenes for those display purposes. So we will choose two components from so many photonic devices, and these two are the first one is this interferometer mesh, and the second one is this micro ring system. So these two are operating, as far as I know, in the different domain, but the functionality is similar. Like we are using the transfer matrix from these optics to arithmetically represent this matrix multiplication in the tensor processing unit. So we start from this MZI implementation. The component for this MZI circuit is this 2x2 conversion, which we can get these three states by controlling the MZI properties. For the two inputs represented by this temporal signal, A1 and A2, we can get this bar state, and which corresponds to the case that the A1 directly goes to B1 and A2 directly goes to B2 as well. And the second state is this cross state where we have this crosstalk so that A1 goes to B2 and A2 goes to B1. And this partial state would be the mixture of the former two states I have mentioned. So this would be depending on the state of this MZI function by our controlling algorithms. So this would get many kinds of functionalities so that it can almost replicate these electrical transistors. So like these electrical integrated circuits, the MZI is implemented on the surface of a chip, but they manipulate light instead of electrical signals. So using this on-chip optical waveguide and beam couplers and these electrical optical modulators, as well as in the later part, we have these photon detectors, and for the input, we have those lasers. So as a representation, we have shown here that because we are implementing this 2x2 matrix for this gate, and also in the lossless system, which is the common case in photonics, we have the unitarity constant. So we actually only have 2 degrees of freedom. So in this case, we would have this eta1 and phi1 to represent the 2 degrees of freedom, but you can also see other degrees of freedom in many MZI meshes. So at the end, we would get a 2x2 matrix from this mesh system, and we would represent by this cross sum so this would correspond to the processor unit, as I have mentioned before, and without going into the detail, we would be able to describe this entire photonic circuits in this very compact and clear way. So to implement a large-scale computation rather than a 2x2 conversion, we need to connect those candle gates into a mesh where there are 2 commonly used meshes. One is called this rack mesh. It is a triangular geometry, and it is easy to implement row by row in this triangular size. So we call and this candle configuration in a row by row manner, we can correspond to those self configuration, which is very important to get this weight calibration for the matrix multiplication purposes. So so one of the important steps to implement a large matrix into those meshes is this singular value decomposition for this rack mesh. And of some matrix of some mass demonstrations, we can confidently say that almost every matrix can be obtained by these kind of triangular meshes. So this is firstly demonstrated by this rack mesh paper. But there are also some shortcomings of this implementation because is actually this triangular mesh is not the most compact one, and we usually need to take a very large space to implement even a small scale matrix multiplication. So it is not ideal because usually we know that for the on-chip implementation, the economic cost is a very considerable factor. So we need to get the best solution using improved mesh. So this is called the Clemens mesh, named after the inventor of this mesh. So the rectangular mesh has a benefit that it is usually more compact. It almost saves half of the space of the triangular mesh. And also we can build it in a more symmetric way so that it's less sensible to those kind of fabrication errors. So it's actually like many people like many digital circuit people, they criticize about the analog device for their fabrication errors. But these Clemens mesh have been demonstrated that it is more robust to those fabrication errors, noise, and also those detection ratios. So this would be very important to get an analog device with more functionalities. So for some of the meshes schematic I have drawn in the last slides, people have actually built in on chip, so that it has been implemented with CMOS compatible manufacturing processes. Um, but the drawback of this is that it's actually a large scale implementation using in general these MZR elements. Even though we have those improved mesh and also some more more advanced algorithm to design the mesh to implement a large matrix with as small elements as possible, it's still quite large scale because it is one concern that this MZI mesh will square would be the quadratically square with this quadratically scale with this input sizes, and also this diffraction limit would require us that the size of the photonic device would be usually on the scale or larger than the wavelengths. So as we can see here, for even a 26 inputs in this paper, we have already gone to several hundreds of microns. So this is not very ideal for the large-scale data center hardware purposes. And also we need to consider that how could we get the more compact structure for the on-chip implementations. So another shortcoming is this thermal optical shifter control, which is used almost ubiquitously in the MZI arrays. This is driven by some electrical heaters to induce a thermal optical phase shift. And this is like it first of all, like thermal process usually dissipates some amount of power, and this is in these demonstrations it's actually quite substantial. And secondly, as we have those thermal process, it's usually slow, very slow, and has a time latency of several microseconds. So since we are arguing that the photonic system can offer a high-speed computation, we will need to reduce those kind of latency time. And what makes things worse is that since the thermal talk can diffuse and the heat is usually a very sensible problem for even for the electrical chips. So that's one thing that we should definitely avoid. So another last part is that this loss system would be depending on those induced phase shift. So this would cause a non-unitary gate. So even though we have like compare with these electrical chips, we are arguing that the photonic chips are usually not so so lossy, but actually this would induce this kind of thermal loss. So it's not ideal. To solve these problems, we propose this macro ring resonator system, which where we can build this frequency conversion represents by those input modes to the output modes. We use a very compact ring system on the level. Oh, you can see it here in the several tens of micrometers level to get thousands of frequency conversion, because essentially the modulation frequency would be modulation frequency numbers would be determined by this frequency synthetic dimension, which I would introduce later. And the main benefit of this system is that the control speed of this modulation frequency would be equal to those free spectral range of the ring. Because for the ring system, for the on-chip implementations, the ring is very small and the free spectral range of the ring is larger. So in that case, the modulation frequency can be very fast, and we can control that to get almost arbitrary frequency conversion, as we would also demonstrate later. So as a background, we need to understand what is the synthetic frequency dimension. So people probably have heard that the frequency counts have been widely used, like for example, in many even for the military purposes, people have used the high precision detections in those optical frequency counts. So each frequency can be well separated, so it forms a ladder, and we call it a new dimension. And this dimension for different modes can hardly talk to each other. So this would be in very obvious contrast with the thermal crosstalk. And on the other hand, by introducing this modulator on the ring system, we can introduce a small shift in the temporal domain, and it would correspond to this frequency shift. And furthermore, by some mathematical demonstration, you can see that it's actually quite substantial, and it can effectively convert the input frequency count to another output frequency count with almost the total fidelity. So suppose that this is firstly demonstrated in this paper, that on the left we have this target matrix, the amplitude and phase, because in many electromagnetic applications, we need to deal with the complex numbers. So for the complex number, we have both amplitude and phase. So on the left, we have this target matrix, and on the right, we have this what we get from the physical system. So these two are quite close to each other, although this target is very random. So it demonstrates that the effective transformation that can be obtained from this matrix system. And consider that we are only using just a 4-ring system in several 10 micrometer scale. So it's quite compact, and you don't need to do much modulation. So it's a promising candidate to offer a very powerful conversion of the frequency modes, and provided that you have the enough bandwidth to get this transformation. So the reason that we are proposing this synthetic dimension is that it's twofold. So first of all, we have a more compact scale. Instead of scaling quadratically with the input size, we are now scale linearly, limited only by this bandwidth. So in that case, we would be able to convert several thousands of frequency by just a few rings. And consider usually the batch size of the data is just in this similar scale. This would be very useful for the machine learning purposes. And secondly, almost the most important thing is that we have a better control speed. So that compared with this MZI thermal optical control, we are avoiding those latency or loss, but we are using a more compact electrical optical modulators at the level of 1 gigahertz, and without consuming the without damaging the unitary transformation offered by this optical transformation matrix. So far I have introduced the two candidates of this photonic systolic array. So now we would like to put it in an ecosystem to consider how we would be able to connect to the TPU system. So we would need to consider, for example, we have introduced this linear part. What is the nonlinearity that can get from the optics? And how can we interface with this digital part to get instructions, and how we would put the algorithm by compiler into the system. This would always be the concern of our system to be useful. So the first, almost the most important part is this nonlinear component. It's firstly got the result from Dr. Ian Williamson. So he has proposed that this optical nonlinearity using some diode components, and which is very effective and also can get almost arbitrary nonlinearity using a very simple manner of by this optical to electrical conversion. So this is very feasible as well as effective to get this optical nonlinearity in the machine learning neural networks. And another part, as we have mentioned, is that how can we get the instruction and how can we interface with the compilers. So there are two parts, because in the ring, in the interferometer mesh, we have this 2D mesh, and we would have this input from this fiber, and also this readout circuitries. And also we have this control unit for this 2D mesh to get this instruction, as well as this reconfiguration for those high-speed implementations. And more importantly, recent years we have noticed these transformers. So it's also important to get those dynamic reconfigurations into the system. So on the second part, we have this ring system, which is connected by a row. So it's actually you have less control units instead of those 2D systems. Because each ring can get one transformation matrix, and depending on how many control tones you have, you can connect those one after another, and you can configure that also in those self-configuring ways. So you can, in that case, it's actually easier compared with this MDM mesh, and you can get the, for example, if you have the 4064 inputs, and you can get it in a 1 millimeter level to have several rings, and you have like 30 level on these control units, and also to get these reconfigurations I have mentioned for the transformers, you need to get those phase shift controls and to obtain some of these instructions from the CPU. So it is actually to realize some limitations, because in order to maintain a good efficiency, we can some kind of like use this as a coprocessor of the CPU, so that the instructions can be fed from this CPU system in order to be more compatible. So and also we have, so connecting with other systems such as those packaging and also those control software is also an important consideration. So we will need to have those data interface with its off-chip memories, as well as some packaging to enable the good interface with the digital parts. Because as we have mentioned that most of the instructions will still need to get from the digital parts, and also in some implementations, we still need to get this activation from the digital parts. So many interface with the digital parts would be in important consideration. So this is one developed kit we have shown here, but there are certainly some limitations. For example, in the current photonic design, we still are not having domain-specific languages, so that it's not so efficient to get a good design to get all the compiler, all the interface, things like that. And also, we would like to have configuration libraries, also a rerouting algorithm for developer kit purposes. So this would be useful if we are building this photonic system more compatible with the own characteristics of this system, not to still relying on some general languages such as C++ or Python. But this would be a long-term purpose, not in the near term. So as we have shown, we have seen in many applications, if we are building like for example, a wall recognition chip, we would need to combine many components together, such as those linear components as well as nonlinear part, as I have mentioned from Ian's work, as well as some like this scaling part, because one concern from this analog chip is that if you want to convert into a digital to analog conversion DAC, those DAC usually has a limit on the scaling. So you need to firstly convert it down and then amplify it, or sometimes you need to amplify first to get the high precision and then to scale it down later. So those are detailed considerations that would be along the line of the processing units using optics. And also we have this accumulation part which we have used from this systolic array, which can be implemented in a parallel manner. So this will be very efficient. So previous work like have definitely shown some stacking efforts, but we still see that there are many limitations of their works. For example, their combination of this digital chip and the optical chip are quite rough. So in the current demonstration, we have seen no significant advantages compared with the electrical chips, and also this stacking manner is not using any high bandwidth memories as we have seen in the TPU design. Perhaps the most important part is that the digital and optical chip, I think, can be put in the same encoder so that you would be able to have a more efficient communication between the electrical and optical parts. And also, as we have mentioned before, since their chips are using this MZI, so their thermal optical control are certainly not optimal. So the control latency are significantly damaging this chip performance. So we cannot see a good advantage compared with this optical, as we have shown theoretically. So we would like to improve this chip significantly from both the interface with the digital part and how to stack and package in a more efficient manner, and how we would be able to load data from the memories with less data improvement, with less data movement. So this systolic array would be one way, but we are still looking for other ways to get a better improvement. So as a summary that we have proposed, the main purpose is that to get the photonic matrix multiplication to replace the TPU units in the current very successful implementation. And there are two candidates. The first one is Mach-Zehnder interferometer mesh, and second one is micro-range resonators to get the very efficient and parallel matrix multiplication on chip. And we are still considering how to build an efficient, compatible interface with a TPU system to enable a plug-in optimization as well as the implementation to gather products, maybe almost on the edge TPU level. So I would like to thank Professor Dave Passon and Dr. Martin Schubert for the invitation. And also I would like to thank many of my friends in the group and also outside the group. So thank you for your time and attention, and I'm happy to take your questions. Thank you.
Thank you. Yeah, I mean, let's turn it over to questions. There's a dory, but I see it's empty. So maybe if folks have questions, just raise your hand so we do this in an organized way. Maybe a question from me, if I don't see any hands raised. So there's a lot of, I think, interesting work with quantized and binary neural networks. And I wonder if you can talk about the scaling or the considerations for an optical implementation, optical matrix multiplication, if we care about high precision versus low precision versus maybe extremely low precision.
Yeah, that's a good question. So, so usually we would like to maintain the high accuracy as much as possible. But usually there is a trade-off. You need to get the precision or accuracy as a balance. So depending on the task you have, you can choose for example, to get a high accuracy in detecting those images. Rather than maintain a good high precision. So it's like you need to do the experiment to see after a threshold we can get the relatively good accuracy, and that's already good enough without going to more precision. And what is being seen in the optical domain is that the high precision would usually require the like you need to scale and scale up and scale down. So this amplifier would require a large portion of energy. So it's not very ideal to get the high precision with this cost.
Okay, so basically, for higher precision, we need to provide more power into the system.
Yes.
And yeah. Great.
Yeah.
I think I see, Raj, you turned on your camera. Did you have a question? Maybe not.
Yeah, so I guess if I understand correctly, the primary advantage of going to the synthetic frequency dimension is I guess it's going for a matrix. You want to implement a matrix that's n by n. The space that you need in the MZI case is roughly n squared, but if you're going to the synthetic frequency dimension, it scales linearly with n. Is that correct?
Yes.
But I guess there's a bandwidth concern because the
group velocity dispersion.
Say it again?
Yeah, group velocity dispersion by this bandwidth limit.
Mm-hmm. Mm-hmm.
So this is already considered in the current calculation. So this scale linearly is really limited, already taking account of those group velocity dispersions.
Mm-hmm.
Does that give like a clear practical limit on the size of the matrix?
It's usually on the 10K scale of the matrix we can implement for 1 gigahertz on-chip range.
So it's like a 10K by 10K is where you see a limit?
Yeah.
And I guess another thing is there's this link between the ring free spectral range and the your ring free spectral range has to be matched to your modulation rate and harmonics of it, correct?
Yes. So many modulators can like hardly catch up with this modulation speed. But 1 gigahertz is a conservative estimation of this.
Yeah.
Yeah.
Yeah. Cool. So like, so assuming there's a major advancement in modulator speed, like assuming we can go from 1 gigahertz to 10 gigahertz, how does that affect the, the outlook for the synthetic frequency dimension, right? I imagine it makes it more compact, right? Because your rings can be smaller, right? Larger free spectral range.
Yeah.
Is that kind of roughly how you think it would impact it, or are there other considerations?
Yeah, this is the major consideration we have. Like the size will determine this free spectral range, and the input dimension. This input dimension would increase with a higher modulation speed.
Mm-hmm.
That's a rough estimate. But certainly there would be other fabrication considerations. So what we are talking about is all assuming that the fabrication is perfect.
Mm-hmm.
Maybe one more question from me. I wonder if you can comment on the manufacturing considerations for this TMRR approach and the MZI mesh approach.
You mean the manufacturization?
Yeah. So I mean, if one were to manufacture something like this at scale,
Yeah.
what are the main challenges?
No, the challenges are multifold. So the connection between those rings are one consideration. And the MZI has like if you increase the MZI's consideration is mostly on those skill part. If you have if you want to implement in a large scale, it's very it takes a lot of space and it's not very efficient. And for the ring system, the connection between each ring would be not so easy to implement. And also, you need to control them to maintain the good functionality. To make it to make every ring perfect is very hard. So that's the main challenge of the current implementation.
Okay. Yeah. So just explicitly, like I guess the reproducibility of the waveguide to ring is challenging. I mean, because what you've drawn, I mean, like conceptually, is very simple, and so the challenge in manufacturing it is just in the reproducibility of it, or do I have it wrong?
Yeah, that's the main consideration. And maybe I should add in that if you have this modulator, to maintain a high speed modulation is also the fast. It's also quite difficult to get those kind of high speed.
So I guess from the ring resonator element, there are maybe like ways you could calibrate. Like you could have like these MZI meshes certainly have calibration routines, right? Because there's fabrication errors there. Like, could you imagine similar approaches in the ring resonator element? Like you could, you can certainly tune the resonance of the ring, but I think maybe the coupling to the waveguide also matters. You would also need to tune that perhaps.
Yeah. This tuning of these parameters is very easy to obtain without considering these waveguide details.
Mm-hmm.
Yeah, but could you say that again? Like, what's your detailed considerations?
Well, I'm just wondering if there's like a way of overcoming the fabrication imperfections is you could develop an algorithm to electrically calibrate your hardware, right? So you could calibrate away the shifts in the ring resonance, for example.
Mm-hmm.
Much like in the MZI meshes, you can calibrate away, variations in the phase, right? You can have like a DC phase that you apply, for example.
Yeah, that's right. So the phase is hard to control, and in the MZI, it's easier to get the target modulation. And well, on the other part is a non-convex problem, because you need to find this thermal shifter control. According to the experimental people, this is a non-convex optimization. So there should be some considerations there that are hard to deal with.
Cool.
I see a question came up in the dory from Ryan. Ryan, do you want to just ask your question live?
Yeah, sure. Thanks. This is a really good talk, Lenin. And my question is basically following up the question that Martin had and also Ian had, but I want to tweak this one a little different. If you go to the page 21, so if I understand correctly, and sorry, maybe so like this one, for example, just imagine this is a ring. So basically the transmission you are taking, if this ring has some coupling coefficient shifted, and that will impact the extinction ratio, right? So how would that impact the full performance of your device accuracy? That's my question.
Yeah, that's a great question. So the extinction factor is what? So for the ring system, you also have an extinction factor to evaluate.
Right.
It's
So
actually
right.
not considered here, but I wonder what do you specifically referring to?
So from the ring formula, that transmission, if that's a one ring with the one bus waveguide, then the extinction ratio will not go down to 0 if basically if we don't reach the critical coupling, right? So and it's most likely it's going to shift this critical coupling point, because now the gap between the bus waveguide and ring is going to vary because of the process. But that means our transmission will basically 0 is no longer 0, maybe 10% instead.
Yes.
That's my understanding, right? Like, is anything that that will be dramatically impacted on your accuracy? If that's not
that should affect the accuracy. But it's similar to a loss introduced in the ring system, right? So that the bandwidth become larger. It's no longer a optical frequency count. So we have considered that a loss in the transformation matrix factor, because it doesn't depend on the system. It doesn't depend on the loss without those critical coupling conditions, but rather this can describe the low loss condition as the general temporal couple mode theory can do this job as well. But in terms of if you have a very large loss, that would certainly takes more energy. But in order to get this, in order to get the target matrix, it is capable to compensate those loss with these modulators, because in the modulators we can have gain in the system. This transformation is not depending on the loss of the system, so that you can have we have already taken into account of the loss in the system when we got this transformation matrix. And physically, this system is described by Hamiltonian, and this modulator can introduce a gain in the system. So this gain would be able to compensate the loss in many details of the internal part. So at the end, this transformation will be able to get almost a still arbitrary matrix with high fidelity. So the only limit is that the loss cannot be too large, because the basis of the theory is based on the temporal couple mode theory. So each frequency mode need to be well separated. So if there is a very high loss, and this frequency comb cannot hold, and the temporal couple mode theory cannot be applied as well. So that would be a point to worry about whether the internal loss will cause concern. But since we are working in a regime where the modulation frequency is very large, so that each frequency mode are separated by a very large frequency spectral range. So it's actually easy to avoid those high loss part. So so it's considered a very high frequency spectral range. It's not so easy to get a loss that can destroy this assumption. So in terms of the accuracy we are claiming here, the loss is not a concern.
I guess, is it correct to say that the loss that Ryan was describing would scale all the matrix elements by the same value rather than changing their relative amplitudes? Is that kind of the same thing as what you're saying?
Yeah, the loss is a scaling of this transformation matrix, but we are caring about the relative amplitude,
Exactly.
so it can overcome this problem.
Cool.
Yeah.
So one last question. Thank you for explaining this. So I think my question is also more like does that impact the SNR eventually? It sounds like it's not. It's going to be linear scale.
Yeah, the FSR would not be changed.
Okay, cool. Thank you.
The FSR depends on the size of the ring.
No,
so,
I mean SNR, signal to noise ratio.
Signal to noise ratio is depends on your detector, right? After you have this, although you have this loss in the system that will make the amplitude smaller, but you can amplify it later. So to maintain to overcome this noise.
Okay, thank you.
Cool.
All right, everyone. If there's no further questions, we're just about out of time. So thank you again, Ling Ling, for this talk. It was, I think, really fascinating.
Yeah, thanks, Ling Ling.
Thank you
So much. This is a good talk. Thank you.
Thank you. I'm happy to take further questions if you can email me. Yeah. Thank you very much. Yeah.
Absolutely. Thank you.
Thanks, Ling
All
Ling.
right, folks.